there are one or two things in my slides where I don't have the examples illustrated for corner cases. I'll probably draw them on the board too. That kind of thing's in mind. How many of you have presented papers or something like that before? Out of all 5 of you?
Sure.
Okay.
Previous
The PhD
courses.
students. Okay, yeah, so that'll be an interesting experience then. So you can look at what I'm going to present today as kind of an example of how you can present things. Maybe use it as somewhat of a model. Not many of the graduate courses do make you present things, though, right?
What?
Not many of the graduate courses do make you present things.
I don't know. So far, I took several grad courses, and in many of them I had to present. Well, at least my final project I had to present.
Okay, sure.
Yeah, there are courses where emphasis on the paper reading, and then yes, you have to present paper.
Yeah.
So
Level 8 one, you have to present. Level 7 is basically project.
Okay, that's fair. That makes sense. It's a little odd that we're getting that answer from an undergraduate.
Yeah, here in the course.
Okay.
So what about final project? Are we going to present them?
That's the idea, yeah. So right now I've got the last 2 sessions blocked off for presenting final projects. I may change those into paper presentations or something like that, just so that we only have to go through 2 papers a week ever. And we'll maybe try and schedule final project presentations some other time. I'm not sure about the logistics on that, but I think it'd be rewarding to, see what everybody's done.
Yeah.
I hope. See.
Yeah, so regarding the paper presentations, if anyone wants me to record his or her presentation, ask me. We can put on YouTube, popular YouTube channel. You'll be a star. So yesterday, I get something happened. So Jewish Vegetarian Association of North America, someone from this association reached to me and they said, "Oh, we like your video on YouTube. Can we use it in one of our video presentations?" So they needed some video of human interacting with animals, and they found my video of I'm going to petting zoo and there is cow and I'm touching cow. Interesting.
So it's clearly strictly a research YouTube channel then.
So I have 3 YouTube channels. One personal, one for scientific talks and stuff, and one defined.
Okay. Let's see, 7? I think we'll probably have 9 people show up today. Yeah. One person who's still not quite here yet, and we've cut some more people. Oh well, 8 because we've got 2 who aren't going to show up today. We've added and cut several people. Not sure what that means, but great. It's good all of you are still here. Here, okay. Yeah, we can start. Okay. So I'd like to first recommend again that everybody go to the talk this afternoon by Catherine McKinley. She's one of the big wigs in kind of the program analysis and compilers and runtime systems areas. And she'll be talking about some type-based stuff. We'll talk more about type-based analyses a little bit later on and typing rules and so forth. But the work that I'm going to talk about here is going to be more empirical. We talked about reasoning about program structures, the program internals and whatnot. This is more of a testing-based research paper where we're looking at, we treat the program as a black box. Can we still reason about it in some way? just by feeding in inputs. And before I officially start this off, how many people had a chance to read the paper? Okay, how many people feel like they understood the paper? Okay, that's good, that's good. It will hopefully be clearer. The point is that people will have some lack of clarity when they read the papers themselves, and we work through that lack of clarity together. In part through the presentation, because one person's an expert, and in part through discussion, where we figure out what was unclear and help each other through it.
The worst part was part number 2, where the propositions are described and definitions.
There
was so
yes.
much.
Yes, and I would say that it's opaquely presented, both in terms of needless verbiage, needless explanation for some things, and the notation is just horrible in some places, or at least for me. Maybe it was my PDF, but in some places it was difficult. But we'll work through that. We'll work through that, and hopefully you can see how I present that, and maybe use that as a guide for if you have to face the same thing, how to present it yourself. Okay, so what are we doing? Okay, this is simplifying and isolating failure-inducing inputs. And this is commonly just referred to as a delta debugging paper, or the delta debugging paper, because that's the underlying technique presented here. So the big idea is that bug reports are problematic, right? So if you have some failing input that's reported by a user because something went wrong, they might have some big input that they used in order to make a program behave incorrectly. Maybe it's megabytes, maybe it's gigabytes large. And all you know is that when you pass this large, complex input into your program, you get some incorrect behavior, right? So the problem is that it's difficult to tell what is essential and relevant to the bug. All you know is that you've got this big, complex input. So if, for instance, you've got 3 different bugs, and maybe they all have some commonalities, it's difficult to see these commonalities in the midst of all the noise inside the rest of the complexity, right? You can't see what is essential and relevant. And so you might have 3 different bug reports, and you try and have 3 different people debug each of these, and you waste a lot of resources. It's good to be able to figure out if these reports are really all for the same bug. And even more so, it would be nice if we could make the bug easier to reproduce. It turns out that even reproducing a bug is a very difficult problem in practice. So the simpler you make it to reproduce a bug, the easier you're going to make the debugging process. So what happens if we try to extract the essential relevant portions of these inputs? Well, we might figure out, okay, the red is semi. Can you read the ABC part, Gabby? Okay, good. So we could figure out that, well, the bug is really reproduced just by having some input that says ABC. Pass it into your program, and it crashes. That's much simpler, right? And at this point, we can tell that all of these are the same bug. So we can just have one developer debug one of them with this simpler example. And not only is it easier to reproduce the bug, because you only have to worry about this small input, or maybe this input is actually a list of instructions that the user has to perform. And only performing 3 things is a lot easier than performing 100 things to reproduce the bug. It's also easier to understand, right? Because you have this core essence of what led to the failure, instead of all this noise that gets in the way. So it's easier to understand the bug. So this is the motivation. This is why it would be nice to take some complex input, complex bug report, and reduce it, distill it down to this. The underlying idea here is what we call delta debugging. Taking this complex input and finding some minimal reproducing test case. A nice goal, right? So that's the goal of this work. So if you look at some of the motivation that they had, they mentioned that back when people used Mozilla as Netscape, which was, I guess, a while ago at this point, they were getting off the ground and they said, oh, they have 300 bug reports. That's just so many. Nowadays, it's going going to be an order of magnitude or several more than that, right? But there was just so many that they needed some way of reducing them, or figuring out how they were the same or not. One of the bugs that they had was that you take this HTML over here, you pass it into Netscape, and if you try to print it, Netscape crashes. So how can we try to reduce this to what is essential? And the actual HTML was much larger than this, but it's just a nice clean example for us to deal with, right? How can we reduce this? Well, intuitively, we could just try getting rid of some portion of the input, right? And this gives us our intuition for the approach. We're going to use trial and error, right? So we're going to start off with our failing configuration. Configuration is just the terminology this paper uses for the input, essentially, right? And we're going to remove some subset, that's the capital delta, of this input. And we can look at the individual atomic elements of the input, and those are the small deltas. Okay? So a subset of the entire set of small deltas is going to be a big delta. There are lots of deltas in this paper. Okay, so we're going to try removing some subset. And if we use this new input and the failure still happens, well, now we've got a new input that's smaller. So in that sense, it's better, right? We've got a smaller, simpler input that still reproduces the failure. This is our new failing test case. And we can just iterate on this. We can try to remove another portion until we have essentially a fixed point or have some smallest input that will reproduce the failure. So that's the intuition, at least. Clearer for those who had difficulty with it already? Okay, awesome. We're already moving in the right direction then. So there are a few questions that come up out of this, though. The first that you might reason about is, when do you stop? You could keep repeating for a long time. So when are you going to stop? Or another way of looking at this is, what is our goal? What are we actually trying to get out of this when we minimize the inputs? So the first thought is that we could try to find a global minimum. So what is this? Well, for some buggy input, buggy configuration, C, it is going to be a global minimum if for all other subsets of input that are smaller than this buggy one, those smaller subsets cannot reproduce the failure, right? So what does this mean? There's no smaller input that reproduces the bug. Layman's terms, that's it. There's nothing smaller that reproduces the bug. That means it's a global minimum. That makes sense, right? How many people here have heard about global and local minima before? Everybody? Mostly? Okay, so you know, if we have, say, a wonderful function that looks like this, the global minimum would be down here. There's also another type of minimum where if we have a function that looks like this, we've got a local minimum right here where, well, around these edges you'll be increasing more, right? But we've also got a global minimum down here. There are two different types of minima. But they're still both types of minima. Okay. That's relevant because once we start to reason about global minima, well, we figure out that this is completely impractical. Can somebody tell me why?
Because it's expensive. It's a lot of time.
It's expensive. Why is that?
You have to go through everything to find the global,
Everything. What is everything?
the whole input.
All
data.
Okay. We have to look at all of these potential C's. That's the power set of deltas, of lowercase deltas, right? So the power set is going to be 2 to the size of your input. So you have combinatorial explosion. There are just too many combinations there to test. It's too large, especially if you've got input that's gigabytes large, right? It's ridiculous. It's not even reasonable. So it's impractical. There's just too many things to look at. So instead, we can start to look at local minima. And now we have something where we say, well, we've got our buggy input, and it's going to be a local minimum if for all subsets of your input that are a part of this buggy input, right? those subsets cannot reproduce the bug. What does this say? Well, it means that if we've got some input that is reproducing the bug, we can't find any portion of that input that will also reproduce the bug. Right? So there's no smaller portion of that particular section of the input. We'll see a slight difference in a moment.
So there might be some more input, some more subset of input?
Yeah, so let me draw a diagram then for that. Should have brought an eraser. So one way of looking at that is that if you have some big input like this, maybe you can reproduce the bug with this chunk of the input. Maybe you can reproduce the bug with this chunk of the input. This is still a local minimum if there's no subset of it that can also reproduce the bug.
So I have two questions here.
Sure.
First one is that, is it possible that it produce two different bugs?
Yes, so you have to be careful about that.
Okay, and
Yeah.
second, is it possible that they both have the same code?
We don't even think about the code. They could both be using the same code, yes. So these are just the inputs, right? So the input could affect any portion of the code at all. We don't even consider that. So we treat the program as a black box that we cannot see into. There are techniques that start to look into the program as well, more white box or gray box techniques. We'll look at those more later on. Okay, but intuitively, we can't take anything away from this and still reproduce the bug, so it's a local minimum. Okay? How does this differ from a global minimum? Well, we could zoom in on this and it would be an acceptable local minimum, but it's not a global minimum, right? There is some other possible input that is smaller, but we have to search through all of the other potential inputs in order to find it. So we can reason more locally within a certain range of the input, and it's still acceptable. Do we still have problems with this?
What happens if some other bug causes a crash? What happens?
You have to be very careful about this. You have to make sure that it's the same type of crash at the same location in the program. And even then, that's not always enough. Technically, that's still not a guarantee, but it's often considered best effort, and it works most of the time. Okay, do we still have problems with this?
Because it's still the power of size of the set that is better, I think.
Okay, it's a little bit better, but we still have to worry about all the possible subsets of this. Yeah, so if this is large, then we still have combinatorial explosion. It's no longer based on the entire input, it's based on the size of our local minimum, but we still have combinatorial explosion, yeah. So instead, delta debugging takes another approximation on top of this and says, let's look for a one minimal input. And the idea here is that if we have some buggy input, C, then for any, okay, not exactly right, but if we take away anything that is part of C, we can't reproduce the bug. So we've got this string of characters. If we take away any one character, we can't reproduce the bug. Right? We just reason about one character. That's our guarantee. Now maybe if you take away more than one, you could get something smaller. But we don't reason about that. We only limit our guarantees to, well, you can't take away just one and get something smaller that reproduces the bug, because this helps us avoid the combinatorial explosion. Okay, are these definitions a little bit more reasonable then? Okay.
So one minimal, it's easier to process than finding a local minimum?
Yes, because we don't have the same guarantees. So consider this. An easy way to check for one minimality is take your local minimum and just one at a time go through every character in that, or go through every delta in that, and see if you can take it away and get something smaller. So it's linear.
Right.
Right, so that's great. That's much better than combinatorial explosion. Okay. So this still has a few issues.
So if you take one character at a time, so how the syntax becomes incorrect, right?
We'll get to this later. That's a very good insight. This is going to come up. So bear this in mind.
Is delta not supposed to be with the ones which are syntactically correct in the first place?
There's no guarantee. And we'll see this become relevant in another paper a little bit later in the semester, a week, 2 weeks, something like that from now. There's no guarantee for this version. And this is a substantive limitation. We'll talk about this as well. Okay, so if we have our buggy input, let's suppose that we've got this string, 1, 2, 3, 4, 5, 6, 7, 8, and we pass it into our program, the program fails. And just for purposes of argument, we know that it fails because it contains 1, 7, 8, right? Just for illustrative purposes, we know that. Question is, how can we minimize this to that bug? The first thing you'd probably try to do is a binary search, right? What would that look like? What would a binary search-based approach do?
Separate them into halves.
Yeah, you take your input, you cut it in half, you try one half, you try the other. If you're able to reproduce the bug with half the input, then you just zoom in on that half the input and continue. That's your iterative process. So what happens there? Well, we can strip away half the input, that's the gray. So what's left here is the blue. But we don't have 1, 7, and 8, so it passes, right? Or at the very least, smiley face means it doesn't fail. So we weren't able to reproduce the bug. And if we do the other half, we're still not able to reproduce the bug, right? So what do?
We keep the whole thing. 1, 2, 3, 4, 5.
We could keep the whole thing, but then we have minimized.
One minimum? Can we try?
We take 1, 2 and put it in the second half, take 5, 6, put it in the first half, and then try the process again.
Okay, so this is more in the right direction. We want to think about breaking things up a little.
Two section, maybe like the delta, does it call it delta? Like instead of 2, do it in 4.
So increase granularity?
Okay, right. So for those who remembered what was in the paper, yes, we increase the granularity. We refine the way in which we've divided things. So we have this really coarse granularity, right? Cutting things into 2. And that was just too approximate. Remember, the way in which you approximate something is by grouping things into sets. We've grouped too many things into the same set, and so we can't see into what's relevant and what isn't. So what happens is that we refine the granularity, and we first try, we cut into 4 chunks now, right? We first try the first 2, because they're one chunk. Well, this still passes, so that's no good. We try the next 2, that's the next chunk, that still passes. Next 2, that still passes. The next 2, well, that wasn't so helpful, was it? So,
Oh, actually, you can really.
Do 1 versus the rest.
could you say that again?
It's 1, 2 versus compare 1 subset compared to the whole minus that subset.
Okay, subset subtraction.
Subset.
I like the way this is going, yeah. So, we have to check the complements, is a way of putting that.
Yes.
So we looked at 1, 2. Well, if we think about how this could affect the search space, and this is a search problem, right? It's a greedy search problem. The bug could be in here, or it could be somewhere in here too. So we have to check that as well. We have to check the complements. So we check the complements, 3, 4, 5, 6, 7, 8. Well, that still doesn't do any good for us. We check 1, 2, 5, 6, 7, 8, and suddenly we start to see some improvement, right? This includes 1, 7, 8, so it reproduces the failure. Great. So now, if you were thinking about this in terms of binary search, the next step would be to zoom in, right? So what does it mean to zoom in? We just strip away the portion that was irrelevant, okay? So now we've got this new search problem over just these components. And so the way it actually works is that we'll search this first section again. That might seem suspicious to you, right? We've already done that.
Already done.
Yeah, we've already done that. So let's think about that a little bit later on too. That's an issue you might raise during our discussion. And then we'll try 5, 6. That looks kind of familiar as well. Then we'll try 7, 8. So we did redo work. What was clever about this design though?
Yeah, one less subset?
We had one less subset, and with a just normal binary search, you might tell yourself, well, okay, I took this, and I took some stuff away. If I recurse, if I continue my subproblem down on this, this set, I might repartition things. I might divide things into chunks again. If I do that, I lose the information that I had before about what worked and what didn't. So you can be a little bit lazier this way, keep the partitioning you had before, and it can make things more efficient. For example, we've already done this, right? So we can cache that result. We can keep track of the work we've done and then not run that test because we know the result already. Okay. Well, this didn't do us any good, but if we check the complements now, we get to refine a little bit more. And so we really just ran 2 additional tests because of our clever organization there. We didn't repartition, so we just had to run 2 more tests. And we were able to reproduce the bug with something much smaller. That's nice. Okay, so let's continue on. We check this half, we check this half, and that's all we've got at this point, right? We weren't able to reproduce the bug. So what did we do before when we ran into
Increase
this?
the granularity further.
Right, we increased the granularity. Yes, we're going to break it into 4 chunks again. We look like we're really close though, right? I mean, we just have 1 extra character. So it feels like we shouldn't have many more steps, especially if you're getting tired of this process already. Can we make a guarantee that we don't have much left? No. Yeah, because there's a fair bit of work to get rid of that 1 character. So what happens? Well, when we increase the granularity again, so now we have every delta is its own subset. Every small delta is its own capital delta. We have this, and eventually we come down here, and we recognize that 178 is able to reproduce the bug. So that's great. We found exactly the input that causes the bug, right? What happens next?
We zoom into it?
We zoom into it.
Because we don't know if that's done.
Right, right. At this point, we've found the minimal reproducing bug, or the minimal reproducing input, but we don't know that there's nothing smaller yet. We have to find that out. So we continue on. Remember, we've broken everything into these smallest deltas. So we then do the same process again. We check each individual thing. We check the complements. Now where we go?
This is the minimum, right?
You haven't tried 1 in the combination.
We're not going to try everything. We're just going to follow our process, right? That's part of the niceness of this system, is that we don't have to try everything. I'm going to say that we're done. This is the end of the process, at least. Okay, so what happened here is that once we got down to the finest granularity and tried everything, you could see that we tried removing each individual element, right? That's our 1 minimality. That's the guarantee we're trying to satisfy. So that's how we know we're done. We did this 1 minimality, and we found that we couldn't remove anything. So we're satisfying our 1 minimality requirement. We're done. Great. Okay.
Is it like a better thing to do, like when you're trying to increase granularity, just shuffle it once and then go?
If you shuffle, you will lose that work you've already done. Remember, so one of the nice things that we saw here is that we were able to keep the work that we did because we didn't shuffle. And shuffling is one of the intuitive things that most people think, hey, I'll do that. If you do that, then you'll have to run more tests. Now, there may be some particular problem domain in which it's beneficial, but in general, this has a nicer structure to it. Because you get to be a little bit lazier and reuse the work you did. Okay, so this is the process. Notice I didn't present anything formal to you yet. I didn't describe anything. So now we're going to just discuss how they present the formality in the paper, discuss how they present the algorithm, and hopefully just tie it back to the example so that you can understand how they presented it, but we don't have to necessarily just look at the text to do so. So how many of you read the algorithm portion? How many of you felt comfortable with understanding the algorithm portion? Okay, there's one somewhat, right? The algorithms and the formality can be a little bit more complicated. So one good way of looking at that is how the algorithm is tied to examples. The example we just saw, for instance. Okay, so the big abstraction for this system is that we have this ddmin function, right? And that is what minimizes a particular input or particular configuration C. And really, all this does is call a helper function, ddmin2. This helper function does all of the work. And it does this by controlling two different things. The first is the configuration or test case to minimize. And in this case, what we saw was the configuration. There's 1, 2, 3, 4, 5, 6, 7, 8. And it keeps track of the granularity. So in particular, what we're seeing here is that the size of a chunk is going to be equal to the size of our input divided by the granularity that we pass in there, right? That is n. Okay? And remember, again, this is the, well, this is just how we're dividing things up, right? So if the big delta is, okay, that shouldn't actually be big delta, that should be n. But if n is 4, then we're dividing each of these things into chunks, and we've got 4 of them, right? So we've got big delta 1, big delta 2, and so on, right? Okay, so that's the granularity portion. And we also had complements. The way the paper represented that was with a gradient, or upside down delta. So another delta, right? It's a little bit confusing with the notation there. And you can see this is the complement of big delta 1. Okay, so how does this function work? Well, it has a bunch of cases, and it just recurses the search problem in a different way depending on these cases. So if we were able to find a reproducing test case that is contained in our delta, our big delta, right? Then that means we checked a particular subset and we found something smaller. Great, so we can just recurse onto that, right? So what is this? Well, this is exactly the input we found that reproduces the failure, right? So we're just zooming in on that input. And we are keeping our granularity as it was. Okay, so what happens next? Well, I should actually rephrase this. Our numeric granularity stays as it was, right? And that gives us kind of the other benefits we saw before. So the other case is that maybe the complement has the bug. So if the complement has the bug, then we pass in the complement, easy enough, and then we have this to control our granularity. What does that do? We have max n minus 1 or 2. Why would we do that? What happens if we pass in 2?
And then you have to go all the way to the number of, what do you call something?
Well, so if it's 2, then we'll look at the total size of the input and we'll divide it by 2 again. We'll just divide it in half. So this is, up here we would divide it by 2 when we recurse on a single atom, right? Because we don't have any smaller chunks to consider. So we cut this one in half, that's what this gives us. And when we zoom in on the complement, we know that we do have bigger chunks to consider. So we likely have bigger chunks to consider. There's a corner case. But if we do, then we can use the max to find out what the appropriate size would be. Previously we had n, right? And we took one away by taking the complement. So that's how we keep the same granularity as we refine. And they explicitly do this. So you can see that it was very deliberate that they didn't reshuffle or anything. They had that in mind. And in the last case, okay. The last case says we're just going to zoom in on the same thing.
So the notation is a bit confusing. When you say max of n minus 1 comma 2 in the second DD-min2, the DD-min algorithm is the same. So now instead of 2, you are trying to put that number over there. So it will not give you the complement of 3 in the test case, right? Because 2 means that you are dividing the
Oh, sorry. This should have been n. This should have been n, sorry.
Okay.
Does that resolve your problem? Okay. If this is n, then when we come over here and subtract 1, that decreases the one that isn't in the complement from our sides. Right? It takes it away from our sides. So we still have the same number of chunks as were originally in that complement.
So 1 means that 3 set of 3
Yes. This is what we're getting rid of. Oh, we have A and we have B. Are you referring to a different row?
Yeah, no, I'm talking about, so when you go for B, if dot B, in that case, when you say max of n minus 1 comma 2, what is that number?
This is our new n.
New n, right?
Yeah.
So suppose now if n was 8, like in this example, 8 minus 1 is 7, max of 7 comma 2 is 7, and then if you put...
N is not 8 in this example. So in this example, n is actually 4, right? Because we have 4 chunks.
Right, so 4 minus 1 is 3, 3 comma 2.
And that would give us 3 chunks, right? So that would work in that case. We would still have 3. Because we took away the one for the one that isn't in the complement.
That taking away part has not been written down, right? So you need to say that now your new n is...
That is...
okay.
So this is...
Yeah, okay.
Notationally, the upside down delta is the complement part. So we're taking it away from the input there, and then this is what takes it away from our granularity. Satisfied?
Yeah.
Awesome. Okay. Is it clear to everybody else now, too? Okay. That is a murky part. That is the part that trips people up every single time. Okay. So then, what was this part? We have our input. What's changing? The input isn't changing at all. What is changing? Just the granularity, right? So which step is this?
When we couldn't produce the puzzle, we are increasing the...
Right, we're increasing granularity. We have, in this case, this is if we were able to reproduce it with our capital delta. This is if we were able to reproduce it with our complement of capital delta. So the next thing is if we weren't able to reproduce it, right? It's the natural successor there. Okay, but there is a qualification. The qualification is that we haven't already reached the maximum granularity. So if we haven't reached the maximum granularity and we weren't able to reproduce it, then we increase the granularity. Otherwise, we have our answer. So if our granularity is as high as it can go, and we weren't able to reproduce it, we're done. Okay, so that's the underlying process. That's the whole algorithm. That's it. If we look at this, the worst case is polynomial. And this happens if everything is unresolved or you weren't able to reproduce the failure, all the way down until you increase the granularity to its maximum. And then at the very end, testing the complement succeeds in reproducing the failure. That's kind of counterintuitive. Why is it that testing the complement and having that succeed would be pathological? Why is that the bad case?
In computers, you have to consider more number of cases.
Yeah, so when we zoom in, we're testing the complement. Our zoom in process then is remove one thing from the input and try the whole thing over again, restart. Now, thankfully, we've increased our granularity as far as it'll go, so we'll keep that, but it's still pathological, so we have to do that, that last stage of testing everything all over again. Okay, in the best case, it's just binary search. How does this work? Well, suppose that we test this portion first, right? And we're able to reproduce the bug. We just zoom in on it, and we're able to reproduce the bug. We just keep zooming in on it until we reach down to a single element that reproduces the bug.
24 hours.
Then we've got binary search, right? Because we just keep dividing the space by 2 and zooming in, so it's perfect. It's logarithmic. That's really fast, right? That's certainly better than combinatorial explosion.
Can you explain the notation in the worst case?
Yes, so the worst case, the number of tests is the cardinality, the size of the input squared,
Okay.
plus 3 times the size of the input.
Can you explain that part again? Testing complements succeed. What's the issue with that now?
Okay, so the issue with testing the complement succeeding is that you've increased your granularity all the way. So every single atomic element of the input is its own capital delta. So if testing the complement succeeds, you have to try everything that's not in capital delta, which is the entire rest of the input. So you're just removing a single element from the input, and then you have to zoom in on the rest, which is everything else. It's still a very large input, right? So that's why it's pathological. Okay, what about the minimality aspects though? So these are the performance aspects. But remember, we're making approximations. So how does this affect the quality of our results? When will we only get a locally minimal result?
When locally we want to know?
I would take it in a different direction. There's maybe a more general answer, I think, or a more useful answer we can go for it. So let's look, just this example right here, right? Why might we only get a local minimum? This is the global minimum, right? Why might we not find it?
Because once it crashes, we stop. We don't go any more further.
Yeah, we zoom in. It's greedy. It's a greedy search, right? So as soon as we look at this half of the input and we find something that reproduces the failure, we zoom in on this half, and this half never exists to us again. So that's why we have local minimality. Can you think of a case where we'd only get a 1 minimal input and it wouldn't be a local minimum? Anybody think of what that might look like? This is a case where you'd actually have to search through all of the subsets in order to find something that is a local minimum. It's a little bit tougher to come up with an example for this. And there are people who do debate whether or not such examples exist. But they do. The paper admits that they do, right? It's one of the approximations they mentioned. So let's pretend this is an eraser. And let's consider an input A, B, C, D. This is enough to create the problem here. And let's suppose that our minimal buggy input, our even, let's say, globally minimal buggy input, but also locally minimal, is B and D.
Together or independent?
Together. You need them both. But it can be the case that you have to take away both A and C at the same time in order to reproduce the bug. If you only take away A, the bug no longer occurs. Even though both of these are in there, the fact that C is in there and A is not can mask the bug when you look at a subset of the input. So you have some non-monotonicity. This is a problem because it hides the bug when you look at this, and so you don't zoom in. Right?
One more question.
Sure.
What if you start zooming in and the input will cause different bug?
If it causes a different bug,
So-
then you're not reproducing the one you're interested in. So in the pictures that I showed up here, that would be a smiley face. It's not a failure, it's a different, or it may be a failure, but it's not the one you're
So
interested
you
in.
do binary search and you put AB
Mhm.
and you get a bug, but it's already different kind of bug because you miss.
And that's one of the ways in which this exact example does happen in practice. You're exactly right. One of the ways is that, if you take away A but you leave C, it exposes a different bug, and so you don't reproduce the one you're interested in. Sometimes it masks it in some other way with correct behavior, but it frequently will mask it with a different bug. Okay, so there are pathological cases like that. It's good to think about what affects the quality of the results, how the approximations affect their utility. We aren't getting the global minimum, we aren't even getting the local minimum. So they have several different evaluation cases here, things like minimizing optimizations that are passed to GCC to find out which optimization causes a bug, things like minimizing Mozilla user interactions, and things like minimizing fuzz tests. Anybody know what fuzz testing is?
Including random numbers?
Yeah, just feeding random inputs into a program. So random input, chances are it's not that easy to interpret, figure out what the bug was. So you can reduce it down to something more useful. This is a common strategy when you do fuzz testing, at least nowadays. And there's a consistent trend that they're able to reduce bugs. It's basically what all the graphs show. They're able to reduce bugs.
They're able to reduce input.
Yes, sorry, inputs. Absolutely. Can you describe the nature of these inputs in a way that might affect these results? Maybe this was related to a question that was asked earlier on too.
Oh, syntax thing?
Yeah.
I mean, from what I understood, is that none of them really dependent on user interaction. I don't know how you, even Mozilla browser, how you move your pointer or press buttons is irrelevant. It's only
The sequence of events that you do, let's say you click on this button, then you click on that button and so forth, that's what you can consider as user interaction.
So did they say
It
that?
wasn't, so in my opinion, it wasn't as relevant. So it's mostly you were working with a text, right?
Well, that's the easy way to present it. User interactions are an even bigger burden because when you're reproducing the bug, you have to have somebody do all of those things.
In the papers, they mentioned that they came down to something like 95 interactions from Mozilla.
Yeah.
And then they narrowed it down, so they do matter in a sense.
Yes, absolutely. Because if you have a whole bunch of complex interaction patterns, then the chances of someone manually reproducing the bug properly are low.
Right.
So that is important. But if you look at all of these are very unstructured, right? Okay, fuzz tests are just big random inputs. Their structure doesn't really matter much anyway. A whole bunch of optimizations passed to GCC. That's just a set of things. There's no structure at all, basically, there. It's just a set of command line options.
I have a question.
Sure.
So regarding the syntax thing, if we have an incorrect syntax,
Mm-hmm.
it won't produce the bug.
Right.
So we would say that it's a smiley face because it's not producing the bug.
Exactly.
If we have only the correct syntax, that the bug will be produced that we expect.
Potentially.
So this takes care of itself, the wrong syntax thing.
Not necessarily. So what can happen is that the issue is here. The issue that you're studying is exactly the issue I'm interested in. The structure of your input is very, very relevant. It will affect, one, the efficiency, because if you're not able to reproduce the bug, then you have to increase your granularity and do a lot more tests, right? If you take syntax into account in terms of determining what your lowercase delta is, then you can get by doing a lot fewer tests. So that's one of the ways that this has been generalized and applied to other domains. But it also affects in some cases whether or not you're able to minimize at all because of issues like this, because the structure of the input gets in the way. And this is what we're going to see come into play a little bit more in John O'Gare's paper. That's something nobody's chosen yet. Okay, so we see that it can reduce these inputs. I've actually talked for a lot longer than I intended to, but at any rate, can we think of cases where this may behave poorly? We just answered this, right? If you've got structured inputs, it's not going to behave as well. What do you think about the goal of one minimality? Is that really what we're looking for?
Not really.
Why?
Because our aim is to reduce the size of input and not exactly get the lowest possible input, right?
It does that though. It reduces the size of the input. Or you're saying maybe that's not.
Maybe, so that's not, it does not need to be the global minimum, right? Even if you have reduced it significantly from say 1000 input to 90 inputs, which is manageable, which is good for us.
Sure, and I think one minimality actually expresses that. But I think there's something that it doesn't express too. It doesn't capture a notion of reducing the complexity. It reduces the size, but maybe the complexity of the input is still high. And if we're looking at reproducing a bug more easily, we want to take into account the reduction in complexity as well.
Complexity in time. Like
Complexity in terms of, it's domain specific, but if, for instance, the input were a C program, well, a complex C program might involve loops and if statements and whatnot. If we can reproduce the same bug without loops and without if statements, it's simpler, right? So it's domain specific. It depends on what you're trying to do. But if you want to reproduce a bug in a simple way, then you also want to optimize the complexity of the input. And that's something this doesn't address at all. Well, I'm not sure how many of you read the discussion on Delta debugging that was also linked to on the schedule. There's some interesting issues there that come into play. And this also gets raised again in John O'Gare's paper. One thing I can tell you is that this is a very commonly used technique, and Delta debugging as an algorithm is implemented in a fairly general way as part of the LLVM infrastructure, because they use it to reduce their bugs. And so if you wanted to use this for something, it's already implemented for you pretty conveniently and generally. You could just take that and use it, right? Okay, so that's everything I've got. We didn't have as much time for discussion. This is why I wanted an hour and a half, 2 hour-and-a-half sessions. But I guess try not to be as long-winded as I was for your own paper presentations. We can try to work more discussion into these things. But you can see I asked several questions, that we got some discussion at least.
Excuse me, are we looking at any paper that does the same problem but looks at the problem complexity-wise?
So the Reducing C Bugs paper by John O'Gare, that's on the schedule, does try to take that into account. It doesn't focus entirely on that, but it takes it into account.
Wow, it is, as you said, it is domain specific.
Right, so they have a reducer just for that domain. They made a system for reducing bugs of C, in compilers for C programs. And so since they know the structure of the inputs, they know the semantics, the meaning of the input, they can make that complexity reducer. I agree.
Then you can get a series of papers, one for Java, one for C#, one for...
In theory, I'm actually encouraging another faculty member to maybe approach that on a particular domain that they're looking at. So I like your thinking. It's still taking some convincing on that end. Okay, so has anybody here volunteered for a paper? Almost. So think about papers if you haven't already volunteered for one. We do have volunteers for next week, so there's at least a reprieve.